Welcome to the Biochemistry Investigations into Cellular Respiration Cell Collective webinar. We're going to go ahead and get started. So before we go too far, if you have not created an account on Cell Collective, then it's helpful because it allows you to save your work. So what we'll do is navigate to cellcollective.org. I put a link to that in the chat box. Click on this red Get Started button, and that will bring you to a landing page that looks like this. In the upper right-hand corner of this page, there's a little profile icon. I'm signed in, so you see my name here. If you're not signed in, it will say something like, please sign in to be able to save your work. So hover over this icon. You can either sign in, sign up, or change the language. If you have an account, just go ahead and sign in. Otherwise, sign up. We don't use this for anything other than to create a place for you to store your work so that you can save it and come back at your leisure. Okay, so once we have that started, get my screen arranged here. We're going to start with this activity called Regulation of Cellular Respiration, Investigation 1, Glycolysis. So I'm going to click on that tab. There's an overview here of the lesson. There are some learning objectives. Notice that the audience here says senior undergrad. These lessons are intended for upper level biochemistry courses. If you are interested in using this for an introductory course or a cell biology course, we have another set of cellular respiration lessons that might be more beneficial for you. There is a webinar tutorial on those. You can find it at our Cubes Hub page, which I will talk about later. For now, we're going to start this lesson. We're going to click this big red button that says Start Lesson. That makes a copy so that I can save my work and come back to it later. And then I'm going to click this tab that says Start Here. That enters us into the activity. Activity 1.1 starts out posing a question to students. Why do energy molecules regulate the enzymes of glycolysis? So the next several activities in this lesson are going to get at why energy molecules regulate glycolytic enzymes. To get started, students are asked to answer a few questions, like when glucose is present, HK has a positive effect on G6P production. So they can come over here to the model and they can find HK and look at its influence on G6P. This arrow is green, which indicates it does have a positive effect. And so here we can click true. The metabolite G6P has a negative effect on HK activity. There is a red arrow running from G6P up to HK, and so that is a negative effect. That's also true. G6P has a negative effect on PFK activity. G6P to PFK, that arrow is green. It says negative here, so that would be false. And one more, G6P and pyruvate are metabolites. You can't just tell that by looking at this model. So I'm going to click on G6P, and that brings up information in the knowledge base. And I can see here that glucose 6-phosphate is in fact a metabolite. Can the same be said of pyruvate? Yes, pyruvate is also a metabolite, and so we can answer true for this. You can answer the rest of these questions. These lessons have many questions integrated. We're not going to go through the answers to all of them, but I have answer keys that are available by request through email. So if you intend to use this lesson and you would like answer keys, send me an email and I will get those to you. Okay, students can answer all those questions. The idea is that they get engaged in the model, with the model, and then they're going to go to activity 2. We can save our work, file, save, and then move to activity 2. Here, we're going to run some simulations. So now we can use this model to simulate the behavior. This model has no allosteric regulation, just purely based on the amount of substrate available. So to simulate we're going to start with a high glucose condition, and then we're going to follow that with a low glucose condition. So to start this simulation, we're going to set the simulation speed to 1, which is the default, and then the sliding window to 100. You can move this slider around, or you can double click and set that to 100 and push enter. We're going to set glucose to 90%. So we've got a lot of glucose available. And then we're going to push run and let this thing go. Oops. We also need to check boxes. What do we want to see? We want to see the pyruvate output, and we want to see ATP. So all these instructions are listed here in this panel. And now we can push play, and we're going to simulate what happens to ATP and pyruvate under these high glucose conditions. We'll let that go to about 110 time steps and push pause. You can see the time steps here, or you can see that it runs to 100 and then it resets and will run to 200. And here's our data. Now that we have this, we can push pause. We're going to drop the glucose to 10, move the glucose slider to 10, and then we're going to run an additional 70 time steps. So this drops all the way down to 10. We're going to let that go to about 180, 50, 60, 70, 80. And now we can compare the high glucose condition to the low glucose condition. What we want to do is record our results in this table. So down here, there is a row for no allosteric regulation. There's a column for high glucose condition and a column for low glucose condition. If we just hover over the line here, we can line that up about with 110, and we can see that pyruvate goes to about 45. Its activity level is about 45. So I'm going to click here and just enter 45. And then the low glucose at 180, pyruvate is sitting at about 24. So we'll go like this. I will say that these are not predetermined. These are dynamical graphs. And so every student's numbers will be similar, but not identical. So our numbers here, I got 45 for high glucose and 24 for low glucose. And now we can answer some questions. As is, the model predicts that the cell will respond as follows to glucose availability. Low glycolysis, activity should be under 25%, and high glycolysis, it should be above 40. Low glycolysis when glucose is low, high glycolysis when glucose is high. That is true. In low glucose, we're under 25, and in high glucose, we're over 40. Is there a large or small difference in the glycolytic flux? Greater than 25% is large, less than 5 is small. We are much closer to a large difference than a small difference. And now there is a thought question. At UNL, in the biochemistry course where this is taught, this lesson is started in lecture. So every student has their computer open and they start these activities together, and then everybody stops here and a clicker question is posed on the screen. A lightly exercising muscle will have a relatively constant need for ATP synthesis to keep it functioning well. Would a muscle cell benefit from changing its pyruvate production, glycolytic flux, as glucose availability changes? Explain your answer. Remember that glycolytic flux determines ATP synthesis. So this is posed as a yes or no question. Would a muscle cell benefit? Yes or no? Students answer with their clickers. They can explain here what they think. It's weird. What I think, and then they have a class discussion. What we find at UNL is that students think this is a really good thing, that when there's lots of glucose available, we can make lots and lots of energy, and when there's not much glucose available, there's not much energy available to the cell. At first glance, I guess this seems reasonable to novice biochemists, but through class discussion, they're brought around to the idea that muscle cells need a constant supply of ATP to keep functioning. So this idea that ATP synthesis is dependent on substrate availability is not a good thing for cells. The next several activities in this lesson are designed to underscore that idea, to give them a sense of what homeostasis is in a complex and dynamical system. So I'll show you how that looks here. So after this class discussion, students advance to this slide and they see that there are some regulatory mechanisms inside of a cell. They're asked to answer some questions, but the key here is this second model. So energy charge as ATP goes up and as ATP goes down. When ATP increases, glycolytic enzymes are inhibited. And when ATP decreases, or read another way, when ADP and AMP increase, glycolytic enzymes are activated. These regulatory mechanisms are what will be added in over the course of the next several activities in this lesson. So this is underscored in the class discussion, that there are regulatory elements. So students can answer these questions. Again, I'm not going to take the time to answer all of these in front of you, but I have answer keys that you can request by email. Okay, activity 1.4. Here, students are asked to modify the model and simulate the behavior, specifically investigating what happens when ATP negatively regulates the activity of glycolytic enzymes HK, PFK, and PK. And so there is some background here. There are some notes, but ultimately the students will run simulations. And so I want to show you what this looks like. We're going to select each of these enzymes, HK, PFK, and PK individually. So I'm going to start with HK because it's next in line in our table down here. So I'm going to click on ATP and I'm going to drag an arrow all the way up here to HK. Okay, select one of the enzymes, add a negative regulatory connection between ATP and that enzyme. So I drug from ATP to HK. This arrow is green, so to change that to red, I'm going to hold down the shift key and click on that arrow. And now ATP negatively regulates the activity of enzyme HK. Okay, in the external components panel, we're going to set glucose back to 90. We're going to make sure that our sliding window is still 100. We're going to make sure that ATP and pyruvate are still selected here. And then we're going to run for about 100 time steps, 110 time steps. So we push play. We're going to let this go. 90, 110. Okay. And then just like before, we're not going to clear the simulation. We're just going to slide glucose down to 10% like this. And then we're going to let it run for about 70 more time steps. Okay. Now we can fill in the next row on our table. Pyruvate production is at 40% activity. So HK negative regulation only, we can type 40 here. Out to 180 time steps, pyruvate is 19. So we can put that over here. Okay, record the activity, match the result to the negative regulation only line, only one negative relationship at a time, delete it before adding another one. So now we've gotten our data for HK, we can select this relationship that we made, and I'm just going to push this negative sign to delete that relationship, and we're going to move to the next one, PFK. Before we start, we clear this, and now we can start over and run the same simulation for glucose at 90%, glucose at 10%, and record our numbers here. We would make this a negative regulator like that, and when we're done with the simulations, we delete this one, add one connection to PK, turn it negative, run our simulations again, and then we can delete this element. This will fill out the boxes for the next 3 rows in our table, and it will demonstrate without running through all of it, there is less variation in pyruvate production, particularly for PFK and PK, when there is negative regulation by ATP. So students can observe that. They can answer these questions. Here, there are several of them. And then we advance to activity 1.5. So the idea is we just demonstrated that negative regulation of PFK and PK by high energy charge is effective to stabilize pyruvate production. So what we're going to do is add those components to our model. Here, a connection to PFK should be negative, and from ATP to PK should also be negative. There are a couple other things that students can do. They can annotate some of these components from the model over here. So if they want to add to PK's knowledge base, they can do that. We don't require that at UNL, but if it's something you're interested in, students can read and do that over here. Okay, save our work and continue to activity 1.6. So we've just added the negative regulatory elements from ATP to these enzymes. I should point out, there is no negative regulatory element to HK. If you click on this component, this negative feedback mechanism is not dependent on the energy charge of the cell. We'll see why that is later at the end of the lesson, but for now, we're only going to add them to PFK and PK. Now we're going to look in activity 1.6 at the positive regulation by ADP and AMP. So literally, we are going to do the same thing that we just did, except add positive regulatory elements. So I'm going to drag from ADP, AMP up here to HK. And this needs to be positive. Okay, so we can set glucose back to 90 for high glucose condition. We've still got pyruvate and ATP selected. Our sliding window is at 100. So I'm going to click play and let this run out for 110 steps and then pause. We'll slide glucose down to 10. Went a little too far. We'll slide glucose down to 10 and let this run out like this. Now, out here, pyruvate is 23 and under high glucose and 22 under low glucose. So for this enzyme alone, you can see that under no allosteric regulation, we have wide variation. That variation is decreased when there is negative regulation only. And it is further decreased, and variation is barely visible, when there are both positive and negative regulatory elements at play on enzyme HK. Now we can delete this, select it, and we're going to repeat that experiment with a positive regulatory element from ADP, AMP to PFK, and then we delete that one and repeat the experiment for ADP, AMP to PK. That should enable us to fill out the rest of our table here, and then scrolling down, answer all the questions below here. Once those questions are answered, we can save our work and move to activity 1.7. In summary, in mammalian muscle cells, both PFK and PK are positively regulated by ADP and AMP to provide tighter control over glycolytic flux. In mammalian brain cells, HK is also positively regulated by low energy charge because glucose is the only fuel that can be used to produce ATP through oxidative respiration. So in this model below, we can see the regulatory elements at work in muscle cells and the regulatory elements at work in brain cells. And what you should notice, and hopefully students will notice, is that this arrow from ADP, AMP to HK is present in brain cells and it is absent in muscle cells. We'll look at that a little more later. There are some questions down here that students can answer. And we're going to add some relationships. So we want to add the positive relationship from ADP, AMP to PFK and ADP, AMP to PK. So we're increasing the complexity of the regulation of glycolysis in this muscle cell. Okay. Now, students should be able to answer this original question. Why do energy molecules regulate the enzymes of glycolysis? Primarily because we don't want ATP dependent upon substrate level of substrate availability. We need a constant supply of ATP. All right, 1.8. The next set of activities considers regulatory differences between cell types. So on the right here, we have glucose uptake in muscle cells, and we have glucose uptake in liver cells on the left. Our guiding question now is, why is hexokinase regulated differently than other enzymes of glycolysis? We noticed that in our last model, HK was not regulated by ATP or ADP. Why is that? To answer the question, we're going to compare liver cells and muscle cells. So again, students are going to answer some questions here. Glucose is converted to G6P by GK in the liver. Here's GK, here's G6P in the liver. That is true. Glucose is converted to G6P by GK in muscle. Over here we have muscle, here's G6P, but it is produced by an by a different enzyme, HK. And so we would click false. Students can continue to answer these questions using the model here. After they look into all of this, we advance to activity 9. And we ask the question, can enzyme kinetics help predict what will happen with glucose uptake? So we're learning about differences in different cell types. Now we're going to look at the kinetics of these two different enzymes. Hexokinase will be operating near its maximal rate when blood glucose levels are low, normal fasting. Well, we can look at hexokinase here. It is constant, it's at the same rate, whether you're fasting or after a meal. And so it does operate at its maximum rate. We can click true. Glucokinase will be operating near its maximal rate when blood glucose levels are low. Well, we can look at glucose here is low, and glucokinase activity is also low. It is not operating near its maximum rate, so we would say false. And there are more questions here that deal with enzyme kinetics that ultimately should help students make predictions about the function of glucose uptake in these different cell types. So once they make predictions, we can advance to the last activity in this lesson. So we're going to run a few more simulations, comparing glucose uptake in the liver to glucose uptake in the muscle under different conditions. So to start, we're going to set glucose to low glucose to 100, external component, low glucose to 100. In the activity network panel, we're going to click glucose uptake in the liver and glucose uptake in the muscle. And then we're going to let this run for about 80 time steps. Okay. We'll pause. We can compare this with predictions that we made in the last activity and answer a few questions. Now we can stop this to reset. In the external components panel, we're going to set high glucose to 100 and low glucose to 0. Start the simulation and run for about 80 time steps. There should be an obvious difference between the two. So glucose uptake by the liver is rising at the same pace as glucose uptake in the muscle under high glucose conditions, But in low glucose conditions, glucose uptake in the liver was 0%. There are a few more questions down here that get at this, this difference. So how does glucose uptake affect glycolysis? We're not going to push stop here. We want this data still present. What we want to do now is click glycolysis in the liver and glycolysis in the muscle. So here, if we click glycolysis in the liver and glycolysis in the muscle, we can see that they are very different. For one, glycolysis in muscle is green, which means it's active. Glycolysis in the liver is red, which means it's inactive. So we can see this liver line down here. To see the muscle line, we have to hover over muscle, glycolysis muscle, because it can hide behind glucose uptake. So hovering over the legend here will show you individual components. And then students are asked questions. Probably most significantly, why would glycolysis be active in muscle cells and not in liver cells? And it gets at the function of these different cell types. In liver cells, when blood glucose is high, we don't want to burn all that. We're going to store that as glycogen. But in muscle cells, when blood glucose is high, they uptake that glucose and they burn it through glycolysis and the rest of cellular respiration. This brings us to the end of the investigation into glycolysis. Well, there are considerations for brain cells, muscle cells, liver cells, and the differences between those three cell types. Here, I want to say that at UNL, this lesson starts in lecture. I told you there was a clicker question asked near the beginning, and then students continue to work through this lesson during the rest of that lecture. They never get finished. So what they don't finish is completed as homework, and they have 2 weeks until the next activity or the next lesson on TCA cycle is assigned. So I believe they have a week to finish this, and then after the due date, there will be a class discussion on the models and on the simulation output and how to interpret all of this. And then students are made aware that on the exam, which occurs between investigation 1 and investigation 2, there are questions about this glycolysis model and the simulation output, which motivates students to engage in the content.